Today we are glad to have Professor Jun Zhu from Princeton University. She received her bachelor degree at University of Science and Technology of China and received a PhD degree at Columbia University. She is an expert in two-dimensional systems, especially good at making graphene heterostructure. Today, she will talk about Magnons and valley isospin in bilayer graphene. Without further introduction, the floor is yours, please.
Thanks, Chen-Li, very much for the intro. I want to first thank the organizers for giving me the opportunity to speak here. Can I share my screen now? Okay, excellent. Now let me bring up my slide. Can you see my screen okay?
Yeah, looks good.
Okay, excellent. So, good morning, good afternoon, good evening, wherever you are. So I want to share with you some of our recent work in looking at Magnons, which is a novel excitation. And that's the theme of the summer school this year. And I also want to tell you a little bit about the valley isospin in bilayer graphene. This is a concept that has existed since the beginning of graphene, bilayer graphene. And I want to show you that it really does look like a spin-like degree of freedom with properly defined Zima energies that we can control. And this is a very powerful way of studying fundamental phenomena. So I heard the organizers say that please cue the questions. But if you have an urgent question to ask, please also feel free to raise your hand and I'll do my best. Okay, so since this is a summer school, I'm listing, well, first of all, let me give you a brief overview of what I want to do. So part one of the lecture, I want to review some of the basic knowledge about Bernal stacked bilayer graphene, what its band structure looks like, the Landau levels in the magnetic field. I'll say a few words about how we define the valley isospin, how we manipulate it, and I'll tell you about a very interesting many-body state that happens at the nu equals 0 in bilayer graphene. Turns out it forms a canted antiferromagnet. And it is this canted antiferromagnet with an in-plane rotational symmetry that supports a gapless, linearly dispersed spin wave mode. So the so-called Goldstone mode. And I'll show you how we measure that mode in this system. I'll again step back and very go broadly by telling you a bit about, in general, what is a spin wave and how do we measure its dispersion? Why do we care about spin waves? And I'll show you how we measure the dispersion of this mode in our system. And I'll show you how we understand it, how does it compare to theory, and so on and so forth. Part 3 of the lecture is about the valley isospin. I want to show you that this is such a nifty knob that we can control in bilayer graphene. We've seen a new even denominator fractional quantum Hall state at filling factor nu equals 1/2. And by tuning the valley isospin to zero Zima energy, we can in fact show experimentally that it is spontaneously polarized in this degree of freedom. So that's an important prediction of the Murid state. And then maybe we won't have time, but if we do, I'll show you a phase diagram of the different valley polarization ground states of the conventional odd denominator fractional quantum Hall states. If we don't get there, there was a talk that I gave a few weeks ago at the EPQHS 8 that also was at Princeton, and that talk was recorded, so you can find it on YouTube. Okay, So I listed some of the references here. These are mostly books and review articles that provide a good background for a lot of what I'm going to talk about today. You will see references, individual papers on the slides as well. But books are always easier to read when you start on a new topic. The references at the bottom are work from my lab that have to do with today's lecture. And these two highlighted in red are more recent. One has to do with the spin wave work, and the other one is the fractional quantum Hall state work. So let me start out by telling you a bit about the material that we work with, that is Bernal stacked bilayer graphene. So, well, I start with monolayer graphene, right? So everyone knows that monolayer graphene is a honeycomb of carbon atoms. And that because of the symmetry, the momentum space has two inequivalent points, K and K prime here. So the monolayer graphene has no band gap because of the symmetry between the B1 and the A1 sublattice. Now, if you take two sheets of monolayer graphene and then shift one with respect to each other in the way that I just showed, and then stack on one on top of another, you have Bernal stacked bilayer graphene, also called AB stacking. Now, in today's language, this is a 60-degree twisted system. Right? So this is what it looks like. SiO2, slightly purple. This comes out of a piece of graphite crystal. And if I look at the side view of the atoms that are involved in the band structure, I have two from the top layer and then two from the bottom layer. A1 and B2 are stacked on top of each other. So there's a strong on-site interaction represented by gamma 1 here. And then B1 and A1, of course, there's a intra-layer bonding. Now, this gamma naught, that's the intra-layer bonding, is the largest energy scale here. So in a tight binding model, this is about 3.4 eV. Then the next energy scale that's important is the gamma 1, the on-site energy between these two stacked, and that is about 0.4. Now, this is this energy scale is the difference between the low energy bands, which are these solid lines here, and the higher energy bands. So this separation is given by gamma 1. There are other hopping terms that are important in determining the band structures, and they also appear in various physical phenomena, some of which we will see. The next one that's important is gamma 4. That's between B1 and B2 here. So this term determines the asymmetry between the electron and hole bands in bilayer graphene. As you can see here, my electron bands have a smaller mass than the hole bands. There's about 30% difference between the electron hole band. This is quite different from monolayer graphene. Monolayer graphene is almost the electron hole symmetric. Now, how do we know these band curvatures? We measure them from Shubnikov-de Haas oscillations, and that gives us the mass as a function of carrier density. And I'm showing you here the hole mass and the electron mass. You can see that it's changing with carrier density. So the band is hyperbolic rather than parabolic. And it's only at the very low energy you can approximate it with parabolic bands. And it turned out that works very well for what we are going to talk about today. Almost everything happens near the E equals 0. There is another hopping parameter, gamma 3, that is between B1 and A2. Excuse me. Now these are the two unstacked atoms. So this term leads to what's known as trigonal warping. If you look at the Fermi surface, it's not perfectly round. It looks like a triangle, right? So, and this energy scale is about 0.1 eV in bilayer graphene. So because there is still a symmetry between the B1 and the A2, there's an inversion symmetry between these two sites. And that's where the low energy bands come from. Bilayer graphene intrinsically does not have a band gap. We can create a band gap though by applying an electric field perpendicular through the sheet. And that's done by using two gates that sandwich the bilayer graphene like so. So when I apply an electric displacement field D here, I create two different electrostatic potential for the top layer and for the bottom layer. And that is the origin of the band gap in bilayer graphene. We can measure that band gap by using thermally activated transport. I show you some of the data here. We can map it out as a function of the applied displacement field. And you can see that this almost looks like a straight line, right? So as I apply higher and higher displacement field, I get a larger and larger band gap. And band gap could go up to about 200, 300 milli eV or so, but it wouldn't go further because we do have the gamma 1 that's limiting how big it could be. Now, as we make better and better samples, we can approach the small gap regime better and better. And in our latest samples, this is how it looks. We find that this slope gap energy versus D field is in fact a very good constant in the entire regime. And that constant is 1.4 Kelvin per 1 millivolt per nanometer that we apply. Right? So that is what's going to be the bare Zeeman G factor for the valley isospin. Okay, so now let me put the system in a perpendicular magnetic field, and it's a 2D system. It develops Landau levels, and in bilayer graphene, the Landau levels look like so. And this is the expression of the electron and hole plus minus Landau levels. So I've written out the wave function for the first few. So let's look at, and this is written in terms of the two different valleys, K plus and K minus. Let's first look at the Landau levels with an index that's equal or greater than 2, right? So in this situation. Now, these two bases are the two unstacked atoms that I've shown you before. So these two says that for Landau levels at 2 or above 2, both sites are 50% occupied. And for L equals 2, for example, we have a L equals 2 harmonic oscillator wave function on one side. This is phi square. And then the L equals 0 wave function on the other side, right? 50% weight on each side. And for K minus value, you swap these two. So that's what the wave function looks like. But you can also see that 1 and 0, L equals 1 and L equals 0 are very special in this case. For L equals 0, I put here N equals 0. There is a valley layer locking so that the K plus wave function is entirely on one layer, and then the K minus wave function is entirely on the other layer. You can see that from the drawings. And they take the ground state wave function of the harmonic oscillator. Now for L equals 1, this is almost the case, but not quite. You see that it is indeed L equals 1 that occupies the top layer, but there is a little bit of a component of the L equals 0 that's in the other layer. And then K minus, you swap the position of the the layers. So it's almost valley layer locked, but not quite, not as rigorous as the L equals 0. Right? So this actually came from a four-band model. If you only include these two, and L equals 1 also has the strict valley layer locking. So L equals 0 and L equals 1 are special Landau levels in bilayer graphene because of this. And also because if you look at the expression of the Landau levels, you find that they are degenerate at E equals 0. Above 2, they look kind of like the normal 2-DAG with a parabolic band. But there are, in fact, 8 levels almost degenerate at E equals 0. N equals 0 and N equals 1 is the orbital degree of freedom that we just talked about. And then we have to add the valley, which is the plus minus, K plus and K minus, right? So that's another twofold. And then we have to add on top spin as well, right? So in this, at the starting point, we have a two-dimensional electron gas that has 8 components. Right? Theorists would say this is SU8, but not quite, because you will see that some of these are already broken at a single particle level. Right? But this is a very good starting point to think about this problem. It also says there are a lot of ways of spontaneously breaking the symmetry and order the Landau levels in interesting ways to form many-body ground states. And that's what makes this material very interesting in that regard. So I'm going to be mostly talking about from the experimental perspective. You will hear a lot of theorists in the school. So I'm going to focus on how we can probe these things. What are the knobs that we have for this system? Well, we can tune the Coulomb interaction by changing the perpendicular component of the magnetic field. That gives you a Coulomb interaction energy scale. That's E squared over epsilon LB. LB is the magnetic length, which is the quantity that's changed by B perp. We can tune the Zeeman energy, the actual spin Zeeman energy, using the total magnetic field. So for example, applying an in-plane magnetic field on top of the perpendicular component. Right? Okay. But we can also tune this valley splitting between the plus and minus valley by applying this perpendicular electric field that I just showed you. Okay? Okay. So just like what happens at zero magnetic field, applying a D field perpendicular splits these two levels, giving them a different electrostatic potentials. And that energy splitting is purely electrical. And this is what I call the electric valley Zeeman energy. And the bare Zeeman G factor, the valley Zeeman G factor, as I showed you before, is 1.4 Kelvin per millivolt per nanometer. Right? Okay, so these are the knobs that we're going to be working with. There is also, in fact, a exchange, the E10, right? In the simple model, I just showed you that they're degenerate. The moment you turn on interaction, exchange splits that. It is, in fact, very difficult to calculate from the theoretical viewpoint. It is a small energy scale, unless you're in a very large D field, in which case there are some single particle effect that comes in. So this is dominated, E10 is dominated by exchange, but it also depends on the D field we apply. So you can see that we have these 3 energy scales that we can tune, and that generates very different landscape depending on the order of those energy scales. So I'll give you an overview of what the Landau levels in bilayer graphene could look like. For example, if we fix the magnetic field, right? So we're fixing the interaction and so on. But let's crank up the displacement field. We'll start from D equals 0, where the valley degeneracy is maintained. And I have a small exchange dominated splitting between the N equals 1 and N equals 0. Now let me increase EV from this point down. You can see at some point, these levels would cross, right? So that leads to a gap closing. And after that, we have a different sequence for the Landau levels. So keep tracking the colors and the wave functions of these levels here. So these are the 4. And then I told you that E equals 0 has 8 levels, right? So there are these 8 down here as well. Now, if you are in a moderate magnetic field, it turns out that the Zeeman splitting is very much enhanced by exchange. And that's a very large scale compared to these things. So my 4 levels are in fact spin for all 4 up or spin up, and all 4 below E equals 0 are spin down, the way that what I'm drawing here. But you can keep increasing the valley splitting. At some point, -0 up and +1 down will cross. So that leads to a gap closing for nu equals 0. And then if you keep doing this, -1 up and +0 down will cross. That leads to a second gap closing for the nu equals 0. And then after that, the order of the Landau level no longer changes. And that's what it looks like in the large D limit. Right? So how do I know all of this that I've just described to you? So this is by years of experiments from different groups, including ours. I've listed some of these references here. So I told you that the nu equals 0 gap should close twice at 2 different displacement field. And that's what these 2 displacement field, dH star and dL star, look like as a function of increasing magnetic field. This is our measurements. Now, how do I know that these Landau levels are in fact ordered the way they are? And also, what is the energy scale of E10 and EZ? I told you it's very much Zeeman exchange enhanced, right? So in fact, it's 15 times more enhanced than the bare Zeeman energy. So these knowledge came from looking at experiments, and we developed this effective model in this paper down here in 2018. By looking at a lot of measurements. For example, the capacitance measurement by Hunter et al. This was done at MIT. What you're seeing, these color blocks here are maps of these Landau levels by measuring the polarization. So if a wave function is completely on the top layer, you would measure a large capacitance to the top gate and very little to the bottom gate. If a wave function is partially occupying that and partially occupying the other layer, you will see that difference in the polarization. So by looking at maps like that and how these colors are the same as what we used for these 4 states, one could get the order of the Landau levels. There are also other measurements, for example, measurements of the gap at nu equals 2 as a function of a magnetic field and so on and so forth. So here I've listed some of our measurements and other people's measurements. This is from the Jacobi group. You can see the gap measurements of that. This is our measurements of the E10 as a function of D field and B field. So if we put all of that together, we get back to this level diagram. Right? Okay. This is something that people working on twisted bilayer graphene is actively figuring out. How is the symmetry broken in this system, and what are the energy scales, and so on and so forth. Right? Okay. So this is the effective single particle picture. It gives you roughly what is going on. But there are places where it fails spectacularly. And those are probably the most interesting places you want to look at, because that's where correlation is particularly strong. So for example, if I look at nu equals what happens at nu equals 0, right? So according to this diagram, it says nu equals 0 in the large D limit is valley polarized, right? You can see all the minus signs are down here. And that's also layer polarization, right? So layer polarized or valley polarized at large D field. And if I go to very small D field, less than dl star, right, going towards 0, if I look at the diagram, it says nu equals 0 is a ferromagnet because I have all spin polarization here, right? So, but in fact, it is not. In fact, correlation is so strong at this point, the system rather reorder these 4 levels that are above and below 0. And the outcome is a canted anti-ferromagnet, where the wave function occupies both layers, so no valley polarization or layer polarization. And the spin sector forms a canted antiferromagnet. There is a small component in the z direction along the direction of the magnetic field, but most of the spin component is in plane and it is antiferromagnet. So net spin is 0. And that spin and layer are correlated. You can see that the spin on the top layer points this way and the spin on the bottom layer points that way. So it is a spin valley coherent many-body ground state that spontaneously forms in a non-magnetic system, right? So we're looking at 2 sheets of carbon atoms here. Okay? There's no magnetic moment coming from the atom itself, right? And we're looking at Coulomb interaction, which is very strong in the system because of Landau levels. And at the end of the day, we have ourselves a many-body ground state that looks like it comes out of the textbook of a strongly correlated system, right? Things that you would normally associate with maybe a strongly correlated oxide or heavy fermion system or Mott insulator and so on and so forth, right? So this is quite remarkable that you could just turn on interaction and then come up with a ground state that looks like that, right? Okay, and a lot of that is going on in the flat band systems and twisted systems these days, right? The difference would be that there you have the flat band coming from the magic angle, and here we are using the magnetic field to generate Landau levels, which are the flat bands. Right. Okay, so that's what happens at a very small displacement field, very small valley splitting, and very small Zeeman splitting as well. Right? My perpendicular field is not big. Right? Now, if you now increase the valley splitting, eventually you're going to drive the system into a layer / valley polarized state, like what I'm drawing here, right? Because that's energetically more favorable. So that's this now system now has layer polarization, but the spin is unpolarized, so non-magnetic. On the other side, you can increase the in-plane magnetic field, so you will dial up the spin Zeeman energy, and then these spins will gradually rotate and cross over to a state where all the spins are aligned with the external magnetic field. Right? So indeed, in this limit, you have a bulk ferromagnet, but it has something interesting happening at the edge. There is a pair of counter-propagating edge states carrying opposite spins. So these are looking like a quantum spin Hall insulator, right? With the accompanying edge states, right? So that is the 3 different phases of Bilayer graphene and nu equals 0. Right? So just to show you that it's not just PowerPoint drawings, here's a phase diagram, and this was shown by Kharitonov et al., actually just Kharitonov, back in 2012. He did work both for monolayer and bilayer graphene. And these are the UZ and U perpendicular are the anisotropy energies UZ is in the Z direction. So if UZ is very big, spins would prefer to lie in plane, and U perp is the XY, the anisotropy energy in the XY plane. Right? You can see that how these, as these energy changes, the phase diagram of nu equals 0. That's partial polarization, full polarization. We can't really tell from experiments. This is a crossover. The solid line is a phase transition, first order phase transition. And this diagram can in fact be tuned by external parameters. EV is the Zima energy, and EZ is the, EV is the valley Zima energy, EZ is the spin Zima energy. Right? So this is what it looks like in bilayer graphene. Now this is what it looks like in monolayer graphene. Right? There are some similarities. For example, the ferromagnet and the antiferromagnet, these two are similar. But monolayer graphene is a little bit different. Now in monolayer graphene, the valley degree of freedom corresponds to the two sublattices, just the one layer. Right? So you can see how the antiferromagnet look like. Because of there is in fact a gamma knot. This is pretty strong bonding connecting these two valleys together. So there are additional interactions that are important. In those additional interactions that lead to this Kekulé distortion and this charge density wave phase. Right? Charge density wave is electrons spontaneously occupy one sublattice, but not the other, right? So these aren't there in bilayer graphene because there's a very weak interaction between the hollow site B1 and the A2 at the bottom, right? Okay. So that's the phase diagrams, theoretical phase diagrams. So experimentally, this is what we measured in bilayer graphene. And there are a lot of people, a lot of different groups have seen this in their data as well. So I have two axes. The displacement field is on the y-axis, and then the total magnetic field is on the x-axis. Now, if I take a line cut, fixing B total, but running D, I go across these faces. In the middle, where D is small, we have the canted antiferromagnetic phase. That is a bulk insulator. And then we cross the phase boundary into the layer polarized state. That's also a bulk insulator. Now at the phase boundary, because not all places at the sample arrive at this transition point at the same time, what you effectively have is a percolation network of slightly different Ds when you go through that phase transition. So this percolation network supports bulk conduction, and that's why there is a high conductance peak at the phase transition between these two insulators, right? So this has been seen by different groups. Now, if I take a cut in the horizontal direction, where I'm increasing the total magnetic field, and that's the data is shown over here, all the way from 2 Tesla to 31 Tesla. You can see that originally at low field, the conductance is very low. This is the canted antiferromagnet, but as we increase B total, conductance goes towards a saturated value that's very close to 4e²/h. So this is the signature of the helical edge states that I just mentioned. Right? So that's this phase over here. In fact, if you flip the theoretical phase diagram and then compare to what we have, right, it's strikingly similar. In fact, by correlating these two, we can back out all of the important energy scales of the system, UZ, UPerp, and so on and so forth, using the known EV and EZ that we experimentally dial. So this is a strong advantage of bilayer graphene, that we have these control knobs that we can use to tune the phases. Okay, so maybe I'll put in another just thought stimulator here, right? So what I've just shown you is what I call the conventional phase diagram of nu equals 0 in bilayer graphene, right? We in fact found a different type of phase diagram that has a metallic phase region, considerable width, sandwiched in between the magnetic ground states near d equals 0 and the non-magnetic ground state at large d. Right? So how, we don't know what is the underlying physics of this metallic state, but we do know that in order for it to appear, we have to make the HBN thick. So this phase only appears if the thickness of the top and bottom BN is about 60 nanometers. And we normally make a device, as of a lot of other groups, using BN that's about 20 to 30 nanometers, in which case you will see the conventional phase diagram. So this looks interesting because it seems to suggest that screening, which is what the top and bottom gates bring, presumably in these cases, is still playing a very critical role, even at these large distances. Now, you've probably heard about screening of gates play very important roles when they're close to the 2D system, right? Okay, but it seems even at 60 nanometers, it could still make a qualitative difference in terms of generating new phases. So, any theorists in the audience, if you have ideas, I'm very happy to hear about it. Okay. So back to this conventional phase diagram, right? Okay, so this all looks good. Let me just quickly forward those. Right? But I do have one grudges here, which is right. After all, we're all doing conductance measurements here, right? So I've shown you this one has a bulk gap, this one has a bulk gap. How do you actually know the magnetic order in this phase is indeed as my PowerPoint drawing shows? How do you actually know this is indeed a counted antiferromagnet, right? We're not probing the magnetic properties, we're doing conductance measurement. You can't have an STM poking at these atoms because the sample is sandwiched in between two gates. And these are lattice order, long range order on the scale of the lattice site, right? So this is pretty tough to actually prove directly, right? So it turns out that in fact one could, by looking at the excitations of the ground state. Right? So I'll show you a little bit more, but this canted antiferromagnet is an easy plane canted antiferromagnet. It has rotational symmetry in the XY plane. And for any magnetic order that has this rotational symmetry, it supports a gapless, linearly dispersed mode, spin wave excitations. And that is the smoking gun of this phase. If we could measure this dispersion, we can show that this is indeed the magnetic order that's anticipated, right? Okay, so that's what I'm going to do next, which is to show you a bit more about spin wave excitations, not just the Goldstone mode, but what happens in general in a quantum Hall system, and how do people measure these excitations, and how do we measure this excitation in our system. But I want to pause for a second to see if there are urgent questions that I can already address. If not, we will move on to the second part. Good? Okay, all right. So part 2, spin waves, also known as Magnons. They are low energy collective excitations of a magnetic ground state, right? For example, if I have a chain of spins all lined up in the same direction, that's a magnetic ground state. Now, if I flip one of them, the red one over here, that is an excitation. Right? So I've created an excitation. What the system does is that because of the interactions between the neighbors, it perturbs all the spins in the system. In fact, you can see from this simulation that all the spins persist along the vertical axis, right? No, they are no longer pointing up rigid, like the original ground state. So in this way, this excitation is shared by all of the spins. That's why it's a collective excitation in a sense, right? And forms the spin waves. And just like phonons or excitations of a ordered crystal state, magnons are excitations of a magnetic state. And just like phonons, magnons or spin waves have dispersions, and that's the relationship between energy and momentum, and we can use the language of phonons to describe them. So depending on symmetry of the magnetic order, there are generally two types of spin waves. The first type has a gap at k equals 0. And this corresponds to a magnet that has a broken symmetry that is fixed along a particular direction in space, like what I've drawn here. In this case, if you are to flip a spin, spin can only go up or down. So now it has to point down. Okay. Now that costs a Zeeman energy, Ez, right? So that's the minimum energy you have to pay in order to generate this excitation. And that is the gap at k equals 0. On the other hand, if the magnet, if the order preserves a rotational symmetry, for example, if you have an XY or easy plane ferromagnet where the magnetization could point in any direction in this plane here, then to create a small excitation, all I have to do is rotate this vector slightly, right? That's allowed. That's also one of the ground state. So this energy cost could be infinitesimally small, right? If I just rotate it just a little bit, right? Okay. So this kind of spin wave excitations has no gap at k equals 0 in the long wavelength limit. Now, some of you may know that this corresponds to the Goldstone mode. Anytime you have a continuous symmetry, you have a Goldstone mode. And this is what this spin wave excitation is. It also works for antiferromagnets, right? All I have to do is change the magnetization vector into the neo vector of the antiferromagnet. So this is an easy X antiferromagnet. This down here is easy plane antiferromagnet. And generically speaking, you also have these two kinds of spin wave excitations. How do we measure these things? Right? How do we measure the dispersion of a spin wave? Right? Well, how do we measure the dispersion of phonons? Right? So a lot of people might know that inelastic neutron scattering, right, X-ray, is a very important tool in this. Neutrons carry spin. They come in with a certain energy and momentum. They scatter off the magnons. They go out with a certain energy and momentum. Right? So this process conserves both energy and momentum. If you track the incoming and the outgoing neutron, you can back out the energy and momentum of the magnons. Right? Now, for example, this experiment over here maps out the dispersion of the magnons of a particular material, manganese difluoride, which is a easy X antiferromagnet. You can see the gap here, and you can see the dispersion. Okay. You can also do this with photons, because photons also carry energy and momentum. You come in with an incoming photon, and then you measure the outgoing photon's energy and momentum, and you map out the dispersion. Right? So this is called a brilliant light scattering. If you can focus the light and collect the light in a confocal manner onto a particular location of your device, one could even get to submicron spatial resolution. And this allows you to study a ray, a cavity, and so on and so forth, right? Okay. So my spectroscopy and microscopy. But there's a problem with photons. And we all know that photons have a very large velocity compared to the sound or anything else that solid state excitations have, which means to have energy conservation, your delta K is very small. So photons can only probe a very tiny part of the brilliant zone. Whereas neutrons, inelastic neutron scattering could almost probe the entire, brilliant zone, right? But there's also a problem with limitations with the inelastic neutron scattering. Look at this facility here, right? This is Oak Ridge National Lab, right? You need to go to such places to get enough neutrons, right? They're not floating around. You need bulk crystals of considerable weight in this case to gather enough signal. In both cases, you can cool them down. You can put them in a cryostat down to a few Kelvin, no problem. But if you want to go below a Kelvin into millikelvin regime, that's very hard. Right? So they're not very compatible with low temperature studies, very low temperature studies. Okay. So give you an example of what Magnons can tell you. Just like if you map out the phonon dispersion of a crystal, you know all of the interatomic couplings, right? Could map out quite a complicated crystal with a very large unit cell and so on and so forth. You can do the same with Magnons. By using the Magnon dispersion, you can map out the exchange interactions of the magnetic lattice. So here I show a simple Heisenberg ferromagnet. This is the Hamiltonian. We have only one J, the exchange coupling over here. And the dispersion near Q equals 0 is a simple quadratic dispersion. This prefactor D here looks like a spring constant, right? It in fact works like a spring constant for the magnetic coupling. It contains J, contains the S, the magnitude of the spins. And this is something that experimentalists can back out by looking at the measured dispersion. This is for iron, different layer thickness. And that coupling changes. And you can see that comes out of the data of the measured spin wave dispersion. Right? Okay. So you back out the magnetic couplings. You can also see phase transitions in magnetic systems. So I talked about easy X antiferromagnet. So, up-down arrows, okay, over here, right? It has Magnon modes. So for a lot of these materials, for example, the manganese difluoride, if you now apply a magnetic field along the direction of one of the two, at some point, system undergoes what's called a spin flop transition, where they become canted, and the net component is along the direction of the magnetic field, and the anti-ferromagnetic coupled components are now in plane. Right? Okay. So if you look at now the Magnons, the abruptly softens. Frequency of this quickly, very abruptly drops to 0 at this point of the phase transition, right? Because this one, right, supports a gapless mode. So you can use the spin wave dispersion to detect phase transitions in the system. You can do a lot more sophisticated tasks. One could look at frustrated magnetism with spin waves. One could look at spin liquid. And so on and so forth. But what I'd like to go next is to maybe first give a one slide motivation of sort of why we care, apart from the point of view of fundamental physics. Right? We'll continue with fundamental physics, but there is also a technological drive to studying magnons. And that's similar to why we sort of want to study photons. They carry information, right? And this very nicely illustrated diagrams here from this book here shows you how one could inject magnons, spin waves, into a magnonic device. This could be a cavity or array or junction of some sort. And then you can inject it through different ways. You can pump the spin with microwave. You can convert charge to spin and so on and so forth. But you can also use control knobs to manipulate the magnons inside this device. You can couple photons to it, magnetic field, electric field. And then out on the other side, one could detect the magnons by maybe converting it back to charge or using the optical signal, right? So photons coupled to spin angular momentum through polarization, left-hand, right-handed photons. And there are reasons that one might want to look at these for technological applications. Magnons have very short wavelengths compared to photons, could be tens of nanometers. So you might be able to pack it denser into a device geometry, higher density. If you're looking at an insulator, for example, a ferromagnetic insulator, IG, yttrium iron garnet is an example, or if you're using an anti-ferromagnet, these are insulators, there's very little dissipation, right? These are insulators. So unlike ferromagnetic metal, which has a lot more dissipation, so there is an advantage in thinking about using these materials to do what's called Magnonics. The magnons have fast dynamics, so their frequencies are typically high, especially the anti-ferromagnet magnons, as you can see from the previous slides. Right? So this means if you're making gates out of these, you could have a fast clock. So these are the potential technological prospect. But I want to get back to fundamental physics, right? So I work on two-dimensional electron systems, gallium arsenide in the very past, now graphene. So these aren't magnetic, but if you put a perpendicular magnetic field, they form Landau levels. And as I mentioned earlier, these are flat bands that supports very strong interactions. For example, if you look at the μ=1, the last Landau level of a two-dimensional system, even if you have a very small Zeeman energy, because of that interaction, spins would spontaneously polarize into the same direction. So you got yourself a ferromagnet. And these are called quantum Hall ferromagnets because the driving force comes from the strong interaction in the system, right? Spontaneously polarized. I can create a neutral excitation in the system by flipping a spin like so, right? And out comes a dispersion of that spin wave. Okay? We talked about at k=0, it is gapped by the Zeeman energy, right? Because we have a EZX ferromagnet pointing along the direction of the magnetic field. If you go to the very large K limit, and that's a short length scale, you get back to this local excitation. Now that costs you an exchange energy, exchange between the neighboring spins. So that's the large K limit. I can also create a charge excitation in the system, right, by deviating slightly from μ=1, μ=1 plus a little bit. So now that electron has to occupy the empty Landau level, and that carries the opposite spin. Right? Okay. So all of these, this filled Landau levels carrying all of the spin suddenly sees this spin in the opposite direction. they would like to string it, right? Because there's a strong exchange coupling between. So far away from this red spin, all the spins in the field Landau level are still pointing down. But from the center of this red spin, you can see that all of these guys, in fact, point along the direction of that excitation. And then they gradually rotate to the down position as you move away from that center. So this spin texture could be big, could be small. It's called a skyrmion, right? A large skyrmion means stronger interaction. A smaller skyrmion is a smaller exchange interaction, right? So very interesting spin textures this way. And all of this physics is relevant for twisted bilayer systems as well. There your Landau levels come from a different origin, but nonetheless, similar spontaneous symmetry broken comes into play. So all of this is something that you will hear later, I think, this week from speakers who discuss the twisted systems. Okay, it could be even more interesting. So that was nu equals 1. Right? So in fact, one finds even more exotic excitations at fractional fillings of a Landau level. For example, nu equals 1/3. So a lot of people might have heard of the fractional quantum Hall effect. I hope you have. That carries a fractional charge and fractional statistics. So it does so because the wave function has an interesting nodal structure that supports that. What is less known is that the same wave function structure also supports elementary excitations called magneto-rotons that are exotic as well. Right? So, and this is a theoretical plot of what magneto-roton dispersions look like. So this is k equals 0. You find the Zeeman gap. But focus on this minimum here, the local minimum in the dispersion over here. This is called the roton minimum. It's called a roton because it resembles the roton minimum of superfluid helium, which also has a low point in the dispersion at a finite k. Now, in this case, the roton minimum is bound state of quasi-electrons and quasi-holes orbiting each other, right? So neutral excitations. And there is a particular interparticle distance that minimizes the energy of the state. And that separation between the electrons and holes is given by this nodal structure of the wave function. So it's another manifestation of this interesting wave function that fractional quantum Hall effect has. If you can measure it, that would be great, right? But you can also see how it might be a challenge, right? So fractional quantum Hall effect often happens at millikelvin. You need a magnetic field. Right? Now you're talking about a cryostat, a solenoid, and the samples, if this is graphene and so on, could be only having an area of 1 micron squares and 1 layer of atoms. Right? So if you think about the light and the neutron scattering that I've shown you earlier, you quickly realize it's very challenging to adapt those measurements to a specific sample like this, right? And the conditions of the experiments. So what do you do? So over the years, there have been some very specialized techniques that are developed to probe these fundamental excitations, not only the magneto-rotons, but other spin excitations and textures in the quantum Hall magnets. Right? So for example, one could use resonant inelastic light scattering. And the pioneer of this is Professor Aaron Pinchuk, first at Bell Labs, now at Columbia. So what Aaron has developed is a Raman scattering that works in a dilution refrigerator, a scheme that uses resonant pumping, uses the band gap of gallium arsenide to pump the photons and then track the energy of the outgoing photon. So here you have the energy resolution from these incoming and outgoing photons. Now, as I said, if you're coming with a photon, it energy momentum conservation says you are only probing a very small delta K in the system. But inevitably, there is going to be some impurity in the sample, in particular short-ranged impurities, right? That provides a large K that could scatter the photon from the gamma point to other points of the momentum space. This is a sort of a self-regulated process where there are large density of states on the dispersion. That's where you gather signal from. So in another word, it probes the extrema points on the dispersion. For example, near K equals 0, and also near the Magneto-roton, and also at large K, right? Okay. So a priori, you don't know what K vector is being used. It's something that you have to use theory to assign the modes to, but it allows you to probe these points. And over the years, there have been a lot of excitations that are probed this way, including the Magneto-roton. Right? So here I show you a data from this paper by Grosshaus et al. You can see the Magneto-roton here. You can see another spin texture that's also probed by resonant inelastic light scattering, right? Okay, so this is one way of doing it.
Excuse me, Professor Zhu. So
Yes.
just a reminder, we probably have like less than 10 minutes, so we can have some Q&A.
Less than 10 minutes. All right, okay, all right, excellent. Okay, so I need to speed up, okay. So, so that's resonant inelastic light scattering, right? Okay. Now there is another beautiful experiment that was done in Klaus von Klitzing's group using surface acoustic waves to provide the wave vector that is needed in order to do this experiment. Right? So it's a microwave experiment, microwave absorption, but one patents these interdigitated figures to provide a wavelengths. And you can see beautiful data here showing you indeed the magneto-rotons of the fractional quantum Hall effect. Right? Okay. But I want to mention something else before I move to our experiment, and that is, transport is really the most compatible experiment with a strong field and low temperature. Right? So can you do this experiment using transport measurement? And there have been a lot of effort in doing this for spintronics and magnonics, and that is using spin Hall effect and inverse spin Hall effect to inject magnons into the material, have it propagate, probe its relaxation lengths, and then use the inverse spin Hall effect to detect the magnons, right? For example, as you can see in this experiment over here. So the gist of this experiment is that somehow you have to create a scattering between the two spin species, and that transfers the angular momentum in the form of spin waves into the material you want to study. But you also have to somehow provide the energy and the momentum, and this experiment doesn't. So it doesn't give you the spin dispersion if this is all you do. Okay. So one more word on the canted antiferromagnetic phase before we look at our experiment. Right? So I mentioned that this supports a gapless, linearly dispersed mode. In fact, Takei et al. Had predicted that it supports spin superfluidity. Okay, so there is a movie that is supposed to show, and somehow it is not showing here, that shows you how when the spin is injected into the CAF state, how the in-plane spins precess to transport that net spin up across the material into the detector side. Right? So if the in-plane spins rotate one way, you send a spin up through, If the in-plane spins rotate differently, you send a spin down through. And if this process happens with global coherence, one could in fact support a spin supercurrent through the system without dissipation. So that would be great. And that's generally known as the BEC of Magnons. And it's something that is being explored in several other magnetic insulators as well. Okay, so I don't have that much time. So I'm going to step through our experiment and show you how we measure this mode. Right? Okay, first device making. Right? So we have developed ways, I'm just going to say that we have developed ways of making devices, graphene devices with multiple layers of gates and with the gates precisely aligned with each other and with well-controlled dimensions. So you're welcome to ask more about it, and I'll be happy to talk to you about the technical details. Okay. So for this particular experiment, we're using 4 layers of gating. So you can see these 1, 2, 3, 4 over here. Right? So the blue outlines outline a dual gated area that we use to define the nu equals 0. We control its filling factor. We also control the displacement field so that we can tune between the magnetic and the non-magnetic phase. That's the area here. So it looks like a quantum point contact in this device. It's a rectangular bar in this device. The QPC doesn't matter, and I'll be happy to tell you more about it or if you want to look at the papers. So don't focus on that. There is a second area, which is controlled by the global graphite gate, and that is put at nu equals 2. Nu equals 2 is spin polarized in bilayer graphene. That's this area that's outlined by black. There is a third area, which is very important, and that is resting on the doped silicon gate. And that's everything outside the white dashed line. What we do here is we heavily dope this area so that it has a very large filling factor and lots of edge states. That is, for example, this area between the black and the blue. This area is doped to about nu equals 20, immediately next to the canted antiferromagnet phase. And that's very important for our experiment. Okay, so we inject the spins by scattering between edge states of quantum Hall edge states that carry different spins. Right? As I show over here, if an electron jumps from the spin up to the spin down, it has to, the excess angular momentum has to go away, and that's being carried away by a S equals +1 magnon into the nu equals 0 region, or any other region we want to study. For example, if we're studying an easy X ferromagnet because the spins are pointing one direction and the excitation costs the Zima energy, that means we have to put a DC bias between these two, and there is a threshold in the DC bias that pays for this energy. On the other side, when the magnons come out, it can be absorbed by an electron, let's say from the down spin, and then it hops to the up spin. Now that redistributes the chemical potential because you can see this edge state flows to 1, whereas this edge state flows towards 2. So now you've created a voltage between 1 and 2. Now, of course, the magnon can be absorbed by other contacts as well. So you have to do this all together. It's a modified Landau Buteyker. For those of you who have done Landau Buteyker, you can probably see how this works. So if you put this magnetic media in a state of an easy X ferromagnet, for example, with all down spins, it only supports S equals plus, right? Because you couldn't go down further. So that means the non-local voltage that we are measuring on the other side has the same sign no matter how the magnons are launched. And that also means the differential signal would change sign. So that's a hallmark of a gapped Magnon spectrum. If we do a differential measurement, scanning the VDC and look at dVNL dVDC, we can resolve individual Magnon modes. And for those of you who have done, for example, tunneling spectra, you can see how this works. You can have phonon-assisted tunneling or Magnon-assisted tunneling, and so on and so forth. And we're able to resolve those modes using this differential measurements. So in fact, the paper, the work that figured out all of the stuff that I've just shown you on the previous slides is the work by Wei et al. From Amir Yacobi's lab. Okay. So in this Science 2018, they described this process and also the formalism for understanding the process. And you can see that indeed, if you probe a EZX ferromagnet, which is nu equals 1 in monolayer graphene, you see this gapped spectrum, and you see also the asymmetry with the differential signal. But this experiment doesn't resolve the momentum of the spin waves. What we have done in our experiment is to make the nu equals 0 into a Fabry-Perot geometry as shown here. So we are launching Magnons by scattering the edge states with different spin orientations on the left, right? And because we put this area at a very heavily doped nu equals 20, the edge states are pushed very close to each other. This does two things. Number one is it greatly enhances the scattering probability so that we're very efficient in launching the Magnons into the nu equals 0 regime. The second thing it does is that it pushes that scattering process very close to the boundary of the CEF region. So let me get back to that. And this is important for launching gapless Magnons. Right? So this is a picture shown by Takei et al. It shows you how spins gradually rotate as it transitions from a up-down orientation to the canted orientation. If you launch the Magnons here, you don't have to pay an energy cost because the spins are nearly in plane. If you launch the Magnons here, you have to pay an energy cost, and then therefore you measure a gapped spectrum. So getting very close to the CEF is very important. The third element that is important is the Fabry-Perot, right? So we have a thing that looks like this. And you recognize that a geometry like that supports individual discrete modes inside the cavity. Whenever we are resonant with it, our spin wave K vector, it is enhanced and we get a peak in our transmission. And by probing these discrete points on the dispersion, we can map out the entire dispersion. And that's the method we used to probe the K wave vector. Now, compared to the EZX ferromagnet, the CEF state supports spins that point this way by rotating one way, and spins that point this way by rotating the other way, right? So if we change the DC bias, we launch these two different kinds of spin waves carrying different spins. What that means is that the non-local signal would also change sign as a function of bias. So we expect VNL itself to be an odd function of bias, and then the differential signal becomes an even function of bias. And that's indeed what we see experimentally. So I show you here results from two devices, and you can see this odd function of VNL as a function of bias. I take the derivative of the blue one, you can see the differential signal. Okay? You can see its symmetry with VDC. You can see that it starts at a very small threshold, much smaller than what the Zeeman energy corresponds to. Okay? And it is only there if we put the nu equals 0 in the CEF phase. The moment we hit the phase boundary, the transitions into the non-magnetic phase, the signal just disappears abruptly. So this tells you that indeed, this is the signal of the magnetic order that we are probing here. You see these very prominent oscillations. These are very reproducible. We see them in multiple devices in different temperatures and so on and so forth, right? They look like so. This is an expanded version of one of the traces. Right? After you stare at it long enough, you say, okay, let's just label these peaks in sequence. And let's plot their energy in DC bias as a function of the mode number. And lo and behold, it fits a straight line and it passes through zero very closely. We always had an intercept, but it's less than 30 micro EV. Right? Zima energy is about 1 milli EV in this system here. Right? So we've done it at different temperatures. That's one temperature. This is a different temperature. Below 2 Kelvin, not much changes really. Right? And we fit this data. We can get a spin wave velocity out of it. For our system, this is about 57 kilometers per second in this particular data set. So this is pretty fast compared to, in fact, spin waves of other anti-ferromagnets, right? The fact that we have a very small intercept here shows you that indeed we are looking at a gapless dispersion. And indeed, the CF has this rotational symmetry. If that symmetry is broken, you would open up a gap. And I see something that's very small in this case. This is probably not surprising in the sense that it's bilayer graphene, right? Vanishing spin orbit coupling, no defect, no other particular junk in the system that would give you a direction. So we have a full rotational symmetry in our system.
Professor Zhu, I wonder whether you will be able to wrap up because of the time constraint.
Okay, all right. So maybe let me skip this one. And let me just show you one slide of theory because I think this is something that is interesting. So we talked about the experiment. So I'll just show one slide of theory of what we expect the spin waves to behave in a hydrodynamic picture. Okay. So I showed you that the spins orient, rotate, precess in plane in order to support the transport of a spin, let's say in the up direction, right? So JA is the gradient of that rotation. It turns out that the velocity depends on two things. Number one is the in-plane spin stiffness. That's kind of the spring constant. Right? The stiffer the constant, the larger the spin velocity. Right? Understandable. It also depends on the inverse of the susceptibility in the transverse direction. That is, if a spin comes in like this, if my spins easily do that, then the spin wave actually doesn't propagate very well anymore because they prefer to lie in plane. That's the stronger interaction direction. Right? So it's inversely proportional to the susceptibility in the transverse direction. And both of these are supposed to be independent of temperature at low temperature. And that's indeed what our data shows. And there are dissipation processes that theory predicts that look like it's also a reasonable description of what our experiments show. In fact, one could make a quantitative comparison between theory and experiment by using these interaction energies I discussed earlier, and then we indeed find that theory and experiments work very well in a good agreement with one another. So we're pretty happy with the results here. And I'm going to skip that because I talked a lot about that. I'm going to skip this. I'm going to skip that. And maybe I'll end on this, just to say that, sorry, I took too much time in the beginning, maybe spoke too slowly, but I hope I gave you a gist of how one could use an all-electrical measurement to probe the spin dispersion of a quantum Hall magnet under challenging experimental conditions, right? Low temperature, strong magnetic field, how we could map out the dispersion with a Fabry-Perot resonant cavity integrated into the experiment. And we think this has a long way to go and could go further into the fractional regimes and to probe other broken symmetry states, other excitations of the system, spin waves and Valley waves. Okay. And maybe I'll end on this slide because Jim Eisenstein is coming after. And I think he's going to tell you about double layer systems. And I just want to put in a sort of a teaser here that the double layer system, in fact, is another system that has XY plane ferromagnetism that supports the Goldstone mode. And you might hear from Jim on these experiments. And I'll stop here and give people a few minutes to ask questions. Sorry about the drag.
Thank you, Professor Zhu, for the wonderful talk. So we have a couple of questions raised. I will read it out. So there's someone asking, how do we measure the value of gammas experimentally? I think it's referring to the very first few slide about the.
How do you measure the gamma?
Yeah, I guess it's asking gamma 0, 1, that kind of value.
Okay, all right, okay. So gamma, okay, so gamma 0 and gamma 4. Right? Gamma 0 you can get from the RPES spectral as well. You get the dispersion and then you can, that's the curvature. Right? Now gamma 4 comes from the asymmetry between the electron and hole mass. We can fit that to get gamma 4. So this is our values. You also get gamma naught from mass as well because that gives the overall band curvature. Gamma 1 comes from infrared measurement because that's a direct transition you can probe. And gamma 3 is from this warping.
Okay.
You can see these references here as well.
So the second question is, what sort of magnitude do you need in your knobs to see this bilayer Landau level closer gap? You mentioned Zeeman is large. That means you need to really crank the valley knob hard. What's the most difficult part experimentally?
Let me show you that diagram again. Right, okay. So let me turn all of this up. So you're right, because Zeeman is large. So if you park at a large magnetic field, you can see the D that we need to apply. But these aren't really very difficult to do at all. Right? You can see that you can see this, my cursor is disappearing somehow. You can see this data of D versus B, and you can see what D is needed. Those are not difficult to do. Those are supported by BN gated samples.
Okay, thank you. And then another question is, could you compare this Magnon velocity with quantum Hall edge state?
Right, so that's an interesting question. So what did so we had somewhere about 60 kilometers per second, right? So that is 6 times 10 to the 4. So in gallium arsenide, that's about the edge velocity of quantum Hall edges in gallium arsenide. In graphene, if you look at, for example, the latest experiment by the Kim group and also by the Sasipik group, the edge velocity is maybe a little above 1 times 10 to the 5 meter per second. So slightly larger than, I think in gallium arsenide, these actually, I take that back. So the gallium arsenide edge state velocity could be 10 to the 4 or low 10 to the 5. Because in the more recent measurement by Nakamura's, if you use the screening gates, you make a sharper confinement potential, the edge velocity does reach 10 to the 5. So generally 10 to the, that order. So these magnons are really fast.
Okay, thank you. And then we got a few more questions. Hello, Professor. You are talking about material with canted spin orientation. What about material that maintain collinear antiferromagnetic order when increased magnetic field?
So, so in this system, right, I'm talking about in monolayer graphene and in bilayer graphene, this canting is unavoidable because in order to get the interaction, we have a small B perp, right? I can tell you in our system, this canted angle with the in plane we calculated is about 20 degrees. So it really almost, right, it's pretty flat. If you want to get to a complete antiferromagnet, you have to go all the way to the B equals 0 limit. And at B equals 0, I believe only in suspended samples one sees some evidence of the insulating state at small d field. In our samples are supported by BN, and others also, you don't really see a good antiferromagnetic state at B equals 0. So in this system, canting is not avoidable. However, the dynamics of the canted antiferromagnet in terms of how it precesses in order to transport a spin through is exactly the same as a completely collinear antiferromagnet. And the symmetry is also the same. So it shouldn't stop you from using stuff you learned from the collinear antiferromagnet onto the system.
Thank you. The other question, on the side where the D-induced gap is shown, it looks as if the gap doesn't vanish as D approaches 0. Is that correct, and why?
So you're asking about this this thing here, right? Okay. So this is a sign of disorder in the bulk. The gap should vanish, except that there is always going to be some fluctuation, right? Potential disorder fluctuation. So even if you have a vanishing gap, let me see if I manage with the annotate thing here. Right. Oh, I can't somehow. So the short answer, my annotation is not working. The short answer is that what you're probing, that 5K there, is in fact some sort of activation that goes across this disorder potential, right? When I say a sample get better and better, it used to be 100 Kelvin. Now it's 5 Kelvin. It's a bulk disorder energy scale that you're measuring. And you can see all the others are sort of, they look like they point to a negative offset, right? That's also because of disorder. If you have a gap and then you have a disorder, it has a bit of a band tail states. The measured gap is smaller than what the theory says by the amount of disorder energy scale.
So our participants really want to know more. We got 3 more questions. Hello, Professor. Is a spontaneous quantum Hall ferromagnets? In the spontaneous quantum Hall ferromagnet, why the spin are all spin down? Oh, you can't hear me?
I couldn't hear the second part of the question.
Oh, sorry. In a spontaneous quantum Hall ferromagnet, why the spin are all spin down?
So I think you're asking about the nu equals 1. Now, the exchange says they ought to align in the same direction, right? But remember, we are, right, there is a symmetry breaker, which is the external field we're applying. So, and that's in the up-down direction. That's why the spins are aligned in that direction.
Okay. Can you measure the dissipation of spin transport in bilayer graphene?
That's interesting. That's the part that I didn't get to because of time. So let me move to that slide, and then I'll show you a little bit. We in fact can through two ways. So number one is I'm having some trouble with my PowerPoint. Just a second. I'm looking for the slide. So can you see the screen? Okay, all right. So dissipation, right? So the Magnons are, the coherence at least, is going away as we raise temperature. And that we can see by looking at the amplitude of the resonant peaks. You can see how fast they dive when we raise temperature above 2 Kelvin, right? Okay. So, and this 4 Magnon process that I've shown you from theory is a good way of dissipating Magnons. So as you raise temperature, you get more and more thermal Magnons, and they basically mix with each other. So you kill all the coherence, and you end up with a background, which is what we end up with at high temperature. Right? So this is something that we could use to probe dissipation. There is another source of dissipation, which we don't quite understand, but it seems to be important as well. And that is shown on this slide, which I didn't talk about. And if you look at the plot at the upper right corner here, you can see that this is a map of the resonances as a function of the bulk filling factor. You can see that everything is steady around nu = 2. And then you can see that as we move away from nu = 2 in the bulk, you can see how these guys are all sort of blue shift, right? It seems like we need to consume more DC bias in order to launch the same Magnon modes. If the bulk is not fully spin polarized. I think this is some sort of an inelastic channel at the injector and the detector, because we haven't changed the nu = 0 at all. We haven't changed the temperature. Nothing is changing. It's just at the injection, we have not full spin polarization. And there is something associated with that as well. And that's something that we hope that theorists could help us understand. And there have been actually works by Alan's group. I don't know if Alan McDonald will talk about it, but there have been groups from works from Alan's group talking about some of these issues. Also issues of what happens if you launch a Magnon from say a ferromagnetic region and you want it to pass through a region with a gapless spectrum. What happens to energy momentum conservation at the boundary? So a junction. And so there are things to look at. There is a lot of stuff, students, there is a lot of things that I didn't talk about, but if you look at our PRX, it's a very long paper with a lot more content in it that you can look at. And I'm happy to answer questions if you email me.
Okay. Do you have any implant dependence of velocity?
Do I have any in-plane dependence? No, we have not tilted the magnetic field.
Okay.
That would be great, because if we could see the crossover, right? If I could sort of think about where that question comes from, if we could tilt the in-plane field, going into the ferromagnetic phase and see how the excitation changes, that would be wonderful. But you notice that that requires 31 Tesla magnetic field. We haven't gotten 31 Tesla since the COVID started.
Yeah, so just one more question just came in. I noticed there was a peak missing at number 10 in the DI over DV near the end of your presentation, hidden by the noise.
Very good eyes, guys, very good eyes. You mean here, right? Right. So we don't know what to make of it because looks like there could be something there. And if we look at other temperatures and the negative side, there seems to be something, but we don't quite know. But it does look like it's skipping something. So that's why we also skipped the number here. Right? You can play with it. You can put it in and so on. In the end of the day, it's not going to change your fitting. Very good eyes.
That's all. Well, it's Zoom, so we couldn't clap, but let's just thank Professor Zhu again for the wonderful talk and all the answer.
Well, thank you guys. Like I said, if you have other questions, and feel free to email me. Thank you. Sorry for running over a little bit. I guess I spoke very slowly today. Bye now.